Okay, so I'm going to take you on a bit of a journey today. So the stories I'm going to start with, this is what I call a quantum catastrophe. Okay, these are quantum versions of caustics, and I'm going to try and take you all the way through to a very classical thing. So this is Fock space, actually, from Leah's talk, remember, where she had a number difference of excitations between her two wells. Actually, that's that coordinate, and this is time. And I'm going to claim that generically in the time dynamics of these things, you get certain structures which are universal. I'm going to try and take you all the way through to something called branched flow. Here you can see electrons, the flow of electrons. This is from an experiment. Well, this is probably a simulation of the experiment because you can see the underlying potential. So this is a two-dimensional electron gas. Electrons injected at a point contact here. You have this basically this random potential underneath, and yet you get these very nice branches forming. This is a picture. So during lockdown, I've started having time to read my Physics Today that I get sent every month. And so I was trying to connect what I saw to this sort of macroscopic phenomena. This is Japan here, and this is the tsunami from 2011. This is the coast of California here. So to any Californians in the audience, you may have known that certain places got a high amplitude tsunami sort of, these branches shot out and had high impacts, and also in places in South America. So I'm trying to connect these two. And I will absolutely need periodically and quasi-periodically driven dynamics to get some of that stuff. Okay, so the people who actually did a lot of the work were my graduate students, Wyatt, who's now in Innsbruck, Josh, who's still with me, and Jesse, who's teaching at Red Deer College. And some connected work, so that's these sort of papers here, some connected work which I won't get onto, but is very closely connected to do with caustics, and the Sine-Gordon model is currently, well, we just had the paper accepted actually with Manas and Aman. All right. So what are caustics? So natural focusing is a very common phenomena. So rainbows, this is where light is focused by raindrops in the air, and you find that if the sunlight's coming over my shoulder, I'll see a strong intensity. Imagine, just forget the bow for a second. If I just look up the sky, there's a particular angle, 42 degrees, where I see a rainbow. Similar effect happens with gravitational lensing, where you have a distant source and the light propagates, but the wavefronts get distorted by intervening mass distributions and maybe dark matter, and you get these focusing events which tell us information about what lies between us and the source. That's a very useful technique in astronomy for understanding weak lensing and so on, for understanding dark matter. Another example of caustics was proposed by Zeldovich and friends in 1981. So they showed that if you start off with an even distribution of matter and you apply gravity and let the thing collapse, you will generically get singularities occurring. And they're called Zeldovich pancakes in various shapes. And they claim that this is the origin of the large-scale structure of the universe. Freak waves are another example where you get these waves that seem to be focused in the ocean. They cause a lot of damage to shipping. So insurance companies, they don't fund me, but I hear that they are very interested in this topic. Tidal bores is another example where you get, if you have an estuary that narrows down, it focuses the tide as the tide comes in, you get this shock wave that can shoot up a river. I think this is the example of the Severn Bore, which is near the University of Bristol, which meant that Michael Berry, it's one of his favorite things, and he studied it a lot, and this turns out to be an example. He showed actually it's an example, it's an analog of a white hole. Okay, so that's a time-reversed black hole, and that inspired me and my student Liam to consider waves near event horizons, so an actual sort of black hole. Also, it turns out that you get a phase singularity. So whereas these other singularities here, these caustics are amplitude singularities, if you blue shift the waves as it approaches the event horizon, it oscillates faster and faster, you get a logarithmic phase singularity. And the way nature deals with that is it produces pairs of particles known as Hawking radiation. And that, we believe, is a very generic effect. Okay, so there's some motivation. Now if If you remember just one thing from my talk, this should probably be it. This is a thing of great beauty. It's catastrophe theory. It tells you that there are, I'm trying to stop myself from getting emotional as I show you this slide. Okay, it tells you that in nature, there's only certain shapes of singularity that are structurally stable. And in one dimension, it's a point. In two dimensions, it's a cusp. In three dimensions, it's a swallowtail or an elliptic umbilic or a hyperbolic umbilic. And these things are, so if you have fine tuning, of course, you can make a singularity a point, but that won't be stable. Okay, so when you introduce perturbations, those things explode, and in two dimensions, for example, they explode into a cusp generically, which is, and the higher ones contain the lower ones. So the cusp is made of two-fold lines. So what happens is you cross one of these lines, the number of solutions change. So this is a bifurcation. And so it goes. As you cross these more intricate structures, the number of solutions change. All right, so here's an example. If you have a coffee cup and you have light rays coming in from the top, they bounce off the back wall of the coffee cup. If this was a perfect parabola, a perfect mirror, they would focus at a point, but it's not, it's a circle. And so that point explodes into something that now is stable, this cusp shape. You can see the envelope of these rays here forms a cusp. This is John Nye's hand, actually, in this picture. So what we can understand is going on is that locally, from a physics point of view, we can locally assign an action. And where you have stationary points of the action, so there's three stationary points inside the cusp, you have three rays, three classical solutions. And as you cross this fold line, two of them annihilate. If you cross this other fold line here, another two annihilate. Right at the most intense part of the singularity is where all three solutions annihilate at once. Okay, so Michael Berry and John Nye in the 1970s and 1980s realized that the natural description of these caustics are in fact, is actually given by catastrophe theory. So this thing is structurally stable in the sense that now if this was a plastic cup and I pressed my thumb in the bottom here, I would distort the side of the cup and this structure would get shifted and changed, but it has integrity. So it's structurally stable. They're also singular in the classical theory. So this, in geometric optics, this line here is actually infinitely intense in the geometric approximation. I should have said on the previous slide here that these things form different classes. So in three dimensions, you have three of them, but you can't smoothly transform one into the other. You can do diffeomorphism, so everything you can do with a rubber sheet, but you can't cut it. And so you can't smoothly transform, so each of these is a fundamentally different object. Okay, and there's some things one can write down that describe these local actions. Okay, I just showed you the cusp, and I said it was this quartic thing, this sort of little double well with these three stationary points. So these are called generating functions, but they're also locally the action, and they get more and more complicated and come in more and more variables as you go up in your dimensions, the number of dimensions you have to explore your catastrophe. Okay, so I said that they were singular in the geometric theory, and but the geometric theory is not the end of the story, right? So we have a wave theory. How can we make a wave theory out of this ray theory? Well, we have the action, so we can do a path integral. Okay, so the first one of these, remember the fold here was described by a cubic action. Well, what we're going to do is we're going to exponentiate it and then integrate over something that characterizes all the paths, which turns out to be this little variable here, S. And so you can think of this as sort of elementary little path integral, but in fact, it's a well-known thing. This is the Airy function, okay? Understood by Airy in 1838 whilst trying to understand rainbows. Okay, so this is well, anyway, these are called the supernumerary arcs and things like that. Well, it took another 100 years for the next one, for people to study the next one, which was Pearcey in 1946. And he understood that the wave function that dresses the cusp, it now bears his name, we call it the Pearcey function. And then it kind of took off. People got the idea and they realized that the higher lying ones, they don't really have names, but this one is the elliptic umbilic. So the elliptic umbilic is now dressed by these wave functions, and these are, because of the structural stability of the underlying caustic, these things are universal. And in fact, the last chapter in the NIST Handbook of Mathematical Functions, chapter 35, is on these objects. Okay, you can think of them as sort of special functions like Bessel functions or so on. These are the wave functions that dress singularities. Of course, things that are singular and have universal properties should have scaling properties, and indeed they do. I'll come back to these. So there's various scaling indices called the Berry indices and the Arnold index and so on. For instance, the Berry index here tells you how things are going to scale as you change the wavelength for the cusp, because there's two directions, there's two different scaling indices for the two different directions. I'll come back to that later. Okay, so that's the sort of background. Let's apply this now to some fun stuff. So for instance, light cones on spin chains. I want to convince you that a light cone is nothing other than a caustic. Okay, so imagine that I'm going to transform my spin chain. Let's imagine it's an integrable spin chain, and I'm going to apply a Jordan-Wigner transformation, and then I'm going to diagonalize that by a Bogolubov transform. So I have my vacuum of my Bogolubov quasi-particles, and I'm going to create a single quasi-particle at an arbitrary position, let's say at x equals 0, and then I'm going to evolve that with time. Okay, well then I can write things in momentum space in terms of my dispersion here. That's going to play the role of my little Hamiltonian, my dispersion of my quasi-particles. Let me now see what's happening in position space. So I'm going to project onto position space. Then this thing turns this, and I'm going to also apply continuum approximation. And what we find then is that our wave functions, function of position and time, can be described by this integral. And here we have this phase, which is basically an action. Okay, it's the integral of this Lagrangian here if you integrate this over time. Now, what do we know about light cones? Is that, well, there's a group velocity of these quasi-particles, and the maximum of the group velocity gives us our Lieb-Robinson velocity, the maximum velocity of our light cone. But these are exactly the conditions for caustics. Okay, so if we take our first derivative of our action here, okay, so we can then relate with respect to k, then we can relate our x divided by t is exactly our group velocity. That's what this condition gives us. This is the condition for classical solutions, of course, where your action is stationary. Now, what happens when we want two coalescing points? That's where you cross one of these, you know, in these bifurcation diagrams, these catastrophes where you cross one of these lines, you have two solutions merging. And so you need to be stationary to higher order. That's what this is. And this is exactly the maximum now of the Lieb-Robinson velocity. So these conditions for a caustic match the Lieb-Robinson bounds. So we really went to town on this. So here's the transverse field Ising model. It has this particular dispersion relation here, and so we can find the generating function from it. And if we plot this thing now in sort of space, here I've taken a particular position at a particular time, and then I'm going to slightly change the position. I'm going to search out the edge of this light cone. So generically, this thing has these two stationary points, but you'll see that they begin to approach each other, and then they merge at exactly the light cone. That's where these two solutions coalesce, and then we've gone outside the light cone here, and there's no longer, this is cutting in and out a little bit. But anyway, when you go outside it, then of course there's none of these classical solutions left. So two coalescing points, we just go to our catastrophe theory and we say two coalescing, oh, that's a fold. Has to be a fold, and it's structurally stable, so we're confident of that, and indeed that's what we get. So this is half the cone, this is position, this is time. If we take a cut through it, we could actually take a cut at any angle, because it turns out the projection of an area function is another area function. Anyway, in this particular case, you can work it all out exactly. This control parameter, this is what our area function becomes a function of. It mixes space and time coordinates, but you can work it out. This is you can actually map this thing for the transverse field Ising model into onto the area function, exactly as claimed. Okay, I won't go through the details of it, but you can see in here that in particular, we get this particular power law. This is a Berry index, and you can see things scale in this ratio as you change the Ising coupling J. I should also say, I'll point out that there's also a network of zeros. These are vortex-anti-vortex pairs inside the light cone, and this is predicted. I should have mentioned it when we were looking at the Pearcey function, for example. There were a bunch of nodes, and those are actually vortex-anti-vortex pairs. So this predicts that they should be inside the light cone. Okay, and indeed, so we can check the scaling of this thing. So this is again this airy wave function which gives the edge, the profile on the edge of the light cone, giving this plotting the period of this predicted area function against the exact solution. One indeed recovers exactly this 2/3 scaling relation, which is the Berry index for the area function. Okay. Now the thing is, you should stop me at this point and say, "But hang, didn't you say that in 2 dimensions, this space-time, that it was the cusp was the structurally stable thing, not the fold? So how come we have these 2 folds?" And indeed, there's this very special symmetry in the transverse field Ising model, which means it's not generic. And we break that symmetry by adding this parameter gamma, which gives us the XY model. And then, so in some sense, we were constrained to have the area function even though we're on each side of my light cone, even though we were in 2D. But once we break that symmetry in the XY model, then we should release it. We should release our constraints, and we should get a Pearcey function. And indeed, so this now is the dispersion relation for the XY model. And this time we find that there are 4 stationary points, okay? And where they merge, we're going to expect to see singularities or our light cones. Okay, so let's see how that goes. And so what I predict here is that you're going to actually get 2 light cones. Okay, so we have an inner light cone, which is going to describe our Pearcey function, and then our 2 outer light cones are going to be area function. So if we plot now, and I plotted over over just half of this thing, this action, and you see inside, generically, we have 4 solutions here. But as we cross this line, 2 of them are going to merge. At the very special point at the origin, all 4 of them are going to annihilate at once. But this guy inside here, which is controlled by the interaction, the close interaction of these 3 stationary points. So we have 3 classical solutions that are interfering under quantum theory. They're interfering in here. And this includes, these wave functions include the interference between these points. We tell our students that the only integral you can do is a Gaussian, right? But this is exactly, for 100 years now, we've known since Airy that we can do better than a Gaussian, a single stationary point. We can deal with two coalescing points, and the Pearcey function is 3, and so on. Okay, so we can do better than just Gaussians. Okay, so inside here, the physics is determined by these 3 coalescing stationary points. As you cross this line here, then 2 of them merge, and finally, the last 2 are going to coalesce as we go outside the final light cone. And indeed, one can map this onto this Pearcey function. Now there's these 2 control parameters, which are given down here, which determine the natural sort of variables to convert this physical light cone into this Pearcey function. We get these 2 scaling things here, which are exactly the Berry indices. This all comes out in the wash. You get this 3/4 scaling in the C1 direction and 1/2 in the C2 direction, the other direction. Well, actually, C1 and C2 are combinations of space and time, so I can't quite associate them with the vertical and the horizontal direction. All right, so that's the Pearcey function. Oh yeah, okay, I'm laboring the point here, but so here, as you plot these 2 different directions, let's call them zeta1 and zeta2. So as we make the system more classical, as we let h bar goes to 0, or in other words, as we let J1, as we let the Ising coupling J get large, everything flows in to the origin here, but it flows in at 2 different rates, which are given by these 2 different scaling, these 2 different Berry indices. So we flow in at 1 speed from the vertically and another speed horizontal. And we can show that comes out when you look at the scaling, these oscillations, these fringes, how they increase their oscillation speed as you change this parameter. Okay, so everything I've said so far was for an integral model. Okay, integral models. How does this stuff sit with chaos? So Leah actually asked, well, what comes next? Well, I came next in the sequence of talkers, but we began to look at this, the case of adding a little bit of integrability. So here we looked at adding some non-integrable terms to the Heisenberg spin chain. And we're going to look at the OTOC in this model. Okay, we've seen quite a lot of the OTOC, and I'm going to make a particular choice of these operators and apply and try and now see if we. So this is going to be mainly numerical now, certainly when we're in the non-integral regime. But we're going to in the integral limit. We're going to show you get the area function. But the question I have, everyone always tells me, oh, but the integral limit's fine-tuned. Well, are these catastrophes going to survive going into the chaotic regime? Let's find out. So the answer is yes, they do. So firstly, here's the edge of my OTOC light cone. Okay, we get this nice area function. Ignore the green dashed line. That's another part of this. This is a piece of work with my colleague Eric Sorensen and his student Jonathan Riddell and my student Wyatt Kirkby. We were interested in a few different things here, but so the black line, the red line is this OTOC, and then this green dash line is sorry, it's not green. The blue dash line is our area function approximation. They gradually go out of phase because we're doing a local expansion at the caustic, the edge of the light cone. We could chase it inside the light cone by doing a uniform approximation, but we didn't go that far. But again, you can map it in the integral limit onto an area function, and this gives you various scaling properties as you go in time and in space and so on that are all predicted by the asymptotics of the area function. And now we can switch on our non-integrable terms here, these extra next to nearest neighbor couplings and so on. And what we find is that indeed, if we go deep, so this is deep into this, so this has been shown to be an ETH limit of this model. We're in ETH obeying in this case, and you can see that essentially you can think of this area function as it's melted away, and what has happened is kind of these nodes here, these exact nodes of the free theory, these interference, effective interference, they've been lifted up. There's still these sort of local minima, but they've been pulled away. But does that happen instantly? Does this instantly vanish as soon as you switch on chaos? Does this node instantly vanish? And this is what we're showing here. And no, it doesn't. Okay, so this area function has structural stability even against chaos. So here I'm plotting the height of the first node, and at first nothing happens. You get this S wave. You get this S-shaped curve. Too much BEC in my head. You get this S-shaped curve, which shows that initially this node very slowly lifts off. And so we take this as evidence of some sort of quantum KM theorem, that there's something that protects that these caustics are deeply connected with the presence of invariant tori in phase space, and they are somewhat protected. They don't immediately vanish. So it's not a sort of a transition, it's a slow thing, at least for this particular model. Okay.
Duncan, sorry, just one question about your previous slide.
Oh, yes.
So here when you say these area functions, these seem to be more properties of free models, right?
Yes.
But if I have some interacting integrable model, then you
question.
Don't get these.
We don't. That's next on our agenda. Yeah. I don't know if you have a beta ansatz solvable model, for example, what happens. Very good question. This point we looked at, these two different points are not we skipped over the beta ansatz, that very special point. But this model, it does have a beta ansatz solvable point in it. Yes.
Right. So for the beta ansatz solvable problem, is there numerics for this? Or,
we haven't done that. Not yet.
Okay.
Yeah. No.
Thanks.
Next time. Okay. So we've seen these caustics in these low-dimensional models. How about if we go to a slightly higher dimensional model? So this is the triple well Bose Hubbard model. And this system, again, is actually chaotic. You'll find a nice review by Lear on it, recent one. So here we have 3 wells in sort of imagining coordinate space, but we're going to look in Fock space as to what's going on. Okay, well, if we conserve our total number of particles, our Fock space has 2 dimensions. So using these coordinates here, these are differences between the numbers in the different wells. Classically, if you look at the mean field theory, so this is imagined starting, so these boundaries here, it's triangular due to the constraints of having a fixed total number of particles. If you let this thing go and evolve it under this Hamiltonian, you find that you get these trajectories. And what do you know? Once again, you form one of these catastrophes. So you can think of this as a quench. We start off with this sort of coherent state, superposition of, in this case, equal superposition of all of these Fock states. And generically, in time, you find you get this elliptic umbilic for this particular initial case. And again, so the mean field theory in Fock space is like the ray theory. It gives singularity. So the probability diverges on the edges of these caustics here. To regulate it, you need to introduce the discreteness of like quantum fields. The fact that particles hop in units, you know, a particle is a lump of 1. It hops around in lumps of 1. When you do that, unfortunately, you probably can't see it on this resolution. So my phase space is actually discrete here. That resolves this singularity. So if you solve the sort of quantum model associated with this, that's what gives, you don't see the discretization. So it's a chopped up sort of wave function, a discrete version of the elliptic umbilic, but everything is smooth in this case. And similarly for the, this is a different initial condition. This time we start with a single state, a Fock state in the middle here. And this time we find that we get the hyperbolic umbilic. So this is a slice at a particular time. You can see now this curved portion here, and then this cusp portion from this guy here at a particular time. So these things following a quench will just happen naturally during the dynamics. And they should, I mean, we claim they're generic features of the dynamics. Okay, so quickly in my last 3 minutes or so, I've got to put in some periodic kicking and quasi-periodic kicking. And we're going to try and get out branch flow. So what is branch flow? It's one of these things kind of where you know it when you see it, but it's yet to get hard and fast. People are still trying to figure out exactly how to describe it, but I said it occurs on multiple scales. It's somehow in the weak chaos regime. It occurs somewhere between integrability and full chaos. We usually need to start with a localized source. It evolves, we imagine our waves evolving in a random potential with repeated sort of small angle scattering. So you can imagine either this sort of random potential in the semiconductor or the seabed. In the case of tsunamis, you get this random sort of small angle scattering. Your energy's got to be much higher than the underlying potential to get this effect. So we're going to ignore backscattering, but we find that we're going to get a proliferation of caustics that develop into these long-lived, stable branches. And I should say that these branches, they don't follow underwater valleys or something like that. They seem to have their own structure. Okay, so what's the unkicked case? Well, we saw this a few times, but in Leah's talk most recently, we had the Josephson junction Hamiltonian. Here I'm plotting. So imagine you have 2 condensates that have never seen each other, and you suddenly put them together. Okay, so they have well-defined numbers of particles, and now they allow these 2 independent condensates that now you allow tunneling between them. Okay, well, what would you do? Well, you might solve the Josephson equations. Each of these lines is a solution of the classical Josephson equations. And you find that essentially this is a bad lens. Okay, this cosine is a bad lens. So generically, we're going to get these cups because we have no idea of our initial phase between our 2 condensates, but we know our relative number. Let's say for the sake of argument, I start with equal numbers of particles in the two wells. I don't need to do that because these have structural stability. I can move it off and you'll still get these structures. Anyway, generically, you'll get these cusp patterns formed. So this is the truncated Wigner approximation, where I sample many solutions, all with different initial phases. Then I generically get these singularities, these cusps. And when I do the 2-mode Bose-Hubbard model that came up in the question session, then everything gets smoothed. So I get singularities when I count the rays. If I go for a particular time and I add up the rays arriving at these different points, so it's a slice of this guy, then I get these caustics. when I go to the quantum field theory, where I take into account the fact that these particles come in units of one, everything gets regulated by that quantization, but I still get some remnants. I get these sort of airy oscillations around these peaks and so on. Okay, so this is what I call a quantum catastrophe. This is the unkicked case. And if you zoom in close to one of these things, so here I'm plotting the Fock space amplitudes, you get back, if you go into the continuum limit, you get back this Pearcey function. If you discretize it enough, you begin swallowing up some of these vortex-anti-vortex pairs. You get these This is nice because you remove all singularities. You've removed the singularities due to the amplitudes, due to the rays, and also in this discretized picture, you remove vortices. Vortices are singularities of the phase. The phase is undefined. But in Fock space, you remove those singularities. There's no place where the phase becomes undefined. Anyway, that's maybe a slightly different story. Let's start kicking it. Okay, so we're going to kick this system. We saw this picture, these series of pictures yesterday. And so you find that so there's a single parameter in the classical model. You get this kicked map here. And as you get K, as it gets greater and greater, you gradually remove all these islands of stability. Okay, so I'm trying to wrap up this conference by making as many references to previous talks. So those who were here last week, David Weld's talk, this is exactly what he's trying to make. He does this delta kicking with these pulses. You put these atoms in this optical lattice, which you kick, you switch on and off periodically, and you can get this this quantum kicked rotor. So we've done this numerically. If you plot the phase now in this quantum kicked rotor as a function of time, you get a big old mess. Okay, this is for a particular set of parameters. Is this the, which is this? Of total, including questions? No, okay, good, then I'm good. If we unwrap this phase variable, as we would have in a particle in a periodic potential, then we see this structure come out. So hopefully you can see here these series of cusps that are being generated. This is the classical rays here. So in the quantum mechanical version, there's two parameters you need. Basically, one of them is h bar, and one of them is the depth of the potential. In the quantum, you can see they match remarkably well, actually. I mean, you could say we're in quite a semi-classical regime here, but so we start off everything in the initial phase lying between minus pi and plus pi, and then we let it spread out. And we get these kind of structures, but we don't really see the branched, what I see here, and this again, it's somewhat, we're just sort of starting on this, so we don't have the final story, but I don't yet see branch flow in here. I think you could argue maybe these are branches, but I see a series of cusps, but it doesn't quite look like the tsunami picture. Okay, so what do you do to get the tsunami picture? So we're going to add some, this is the quasi-periodic finally coming in, we're going to add some incommensurate frequencies. So for the kicked rotor, you can think of these as adding extra dimensions to this probably artificial sort of dimensions. Okay, so we're going to do that, and now we really see the branched flow. Okay, so you can see that these structures appear, and the quantum mimics it somewhat. Okay, you can see these structures. So we're still in the throes of exploring this and understanding really how these caustics, how they get melted by this sort of chaotic effects. In fact, what we'd like to do is come up with some. This is a zoom in, just so you can really see how these things look. You really zoom in. What we're trying to do is figure out the statistics of these branches, doing very sort of back of the envelope type analysis, but we're really at that stage. So there's various, you can cook up various dimensionless things. So for instance, correlation distance of the potential, that's easy with flashing on this cosine. We have the typical length. We're trying to calculate the typical length over which these caustics appear. And then another dimensionless ratio would be our energy to our strength of our random potential and so on. Anyway, this is still early days in that story, but it seems that it seems to be a very universal phenomenon of this branch flow in this weak chaotic regime. Although eventually for long times, these things dissipate, and the number of them you can show decays exponentially. Okay, so I'm done with 28 seconds to go. So what have I told you? I've told you that wave dynamics generically leads to caustics. It just seems to happen in nature, and there's a good reason for that. That's because there is a universal description of singularities given by catastrophe theory. That's the underlying natural theory, and there's certain very special singularities which are privileged by being structurally stable, and those are the things that the Tom Arnold catastrophe theory describes. They come in these classes, which I guess I'm advocating as a form of universality in dynamics. They come in classes with various scaling exponents. That's certainly true for integral systems, and it seems to survive, at least in the weakly chaotic regime. There's lots of fun stuff when you discretize them to get quantum catastrophes, and I'm still playing with those. Where am I going next? We're trying to do a statistical analysis of these branch flow or these rogue waves. One other thing I didn't have to tell you, but if you were wondering, is there a connection between these caustics and dynamical phase transitions? So these are transitions as a function of time. Yes, there absolutely is. And if you want to ask me more about that, I will tell you more about that, but I don't have time to squeeze that in. Okay, so thank you for your attention.
Thank you for a lovely talk. Questions?
Thank you very much for this very interesting talk. So you connected these singularities in catastrophe theory to Lieb-Robinson light cone.
Yeah.
So I'm wondering about this in higher dimensions. So in 2+1D you also have Lieb-Robinson. It's really a cone. It doesn't look like the structure, at least the structure of the singularities you've shown in 3 dimensions. So is this is something going on here, or?
Well, sometimes it can be hard to see. So I don't know. I haven't analyzed the higher dimensions. Certainly, we were able to predict for the XY model that there was this double cone, but they don't look, we had to do some transformation of variables. So normally the cusp, you see this nice curved cusp shape, but it turned out there was a transformation of coordinates that made it not a perfect straight line. So it's possible that these things get distorted, but they should somehow have their fundamental sort of catastrophe essence. So yeah, I would like to guess, but it would just be a guess, that these higher dimensional things could be mapped onto this hierarchy of catastrophes, but maybe there's some special condition that means, the thing is, your initial condition can be rather non-generic. Okay, so it depends what you do for your initial condition to set this off. That may not be a completely generic thing. So there could be special symmetries in your problem, just as one has with the transverse field Ising model that limits the full scope of.
No, I think I see now. Essentially, you're saying there is a transformation that will bring you
the
back
art
to
of the difficult part of catastrophe theory is mapping your physical problem onto these sort of abstract objects. And that's a real art and a skill, which my graduate student luckily had and was able to do these transformations. So yeah, it's not completely elementary.
Secondly, and maybe that ties to another question we had. So I'm about the connection with integrability. So it seems to me this is more a question of transport, the type of transport you have. Either, I mean, isn't it right? It's not that maybe it doesn't integrability versus chaos. It's really more of the type of transport class of the model.
Well, I mean, yeah, I don't know how I don't know how transport is going to appear in these.
I mean, you're kind of looking at how particle moves in some, I guess, in some finite density state. Yeah.
Yes. So I mean, so what I can tell you is that I mean, ultimately, these caustics are connected to invariant tori. So if you have some invariant tori that you're moving along, and now you project, so this is in phase space, and now you project down onto some position plane. Here you're going to have many trajectories. They're winding around and around this torus. At the edges here, you're going to have, for instance, this is the position plane. You're going to have many trajectories that have the same position but different momenta. So you're going to, if you sort of represent the probability, the density of trajectories, you're going to get a sharp sort of peak here, which is what is giving the caustics. So if your quasi-particles are going to be confined on these invariant tori, that is certainly going to limit your transport.
Okay.
And when you break the invariant tori, then they're free. The particles are, a number of things happen. They start interacting, but they're free to sort of fill ergodically in phase space.
Right. Again, then it's a question of interacting integrable, right? Yeah. That's open. But I mean, maybe just slight, and then I'm done. So slightly to rephrase, why do you think it's connected to integrability, right? I mean, you said that these singularities should be universal, so one would expect it also in chaotic systems, yeah?
Yeah, and I don't have a full answer to that. What I can tell is that what I can say is that they have some structural stability to it, but I think it's really the properties of your sort of, so caustics are sort of singularities of your Jacobian, of your mapping from your initial state to your final state. And as long as that is smooth, you can take a little tube of trajectories in your initial state and they focus to a point in your final state. Now, when you have chaos, I think this surface becomes too rapidly oscillating. It's not smooth, and that breaks up these nice sort of smoothness. So it's basically your smoothness of your Lagrangian manifold, I think.
Okay. I see. So the
other questions, maybe?
There's one on the chat.
Yeah, can you read that?
Yeah, so it says, regarding your motivations for caustics and their stability, how does one understand stability to perturbations in the integral or non-integrable models you presented? Well, okay, so for example, in the, if we go back, for instance, to the OTOC case, here, so I was switching on these non-integrable terms. So we just multiply this part by lambda, this part of the Hamiltonian, the interaction part by lambda, and as I gradually switch on lambda, so between lambda equals 0 is the free case, and lambda equals 1, we set to be a particular ETH obeying set of, obeys these sort of parameters. So we smoothly switched lambda from 0 to 1, going from where we still have J1, but we switch off these other terms. And it smoothly, we find that our sort of Airy function seems to smoothly melt. So that's what I meant in this case by stability to perturbations. I hope that answers the question.
Yeah.
It's like in other words, it's a sort of other axis that we're adding here as we add on these extra terms.
Yeah. Sai says thank you. Good. Other questions? Yeah.
For the branching and rogue waves and things like that, I wasn't very clear. There's different physical examples, you know, whether it's electrons in semiconductors or ocean waves. How important is that the system have any nonlinearity in it? Like, for example, if I just had sort of lots of small angle scattering off of smooth potentials, would I still get patterns that look like this? And is it also very sort of deterministic in like the ocean wave case? Is that clear?
Yeah, okay, so I don't have a broad answer for you on the latter part. In the first part, yes, so the model we have with the delta kicked rotor that seems to, I mean, we're trying to get what is the essential physics underlying these things. Delta kicked rotor is a very well understood system, at least by some people, if not me. And so the idea is there, we have free motion, and then we switch on this nonlinear kick. And I think the model one, that there's some models out there for tsunamis where indeed you have free propagation and essentially the same. You have this localized sort of focusing event, some underwater hillock or something that kicks this tsunami and bends its wavefront so that you get these singularities. Of course, there is lots of nonlinearity going on in the ocean. You have Navier-Stokes equations, and this is a large amplitude thing. So you'd imagine that you're in there could be nonlinear stuff going on, but certainly in the delta kicked rotor, it's free propagation between these kicks. So it seems to be enough to have free propagation then kick.
Yeah, I mean, I guess what surprised me, the system on the left there, I think that's probably like Westervelt or someone, or maybe it's a model of some data on quantum wells, where I thought that you could get some of that from just like linearity and certain forms of the potential. Like I wasn't sure that required non-linearity, but it seems
No, it
like
doesn't. So certainly this was modeled. So there was this experiment by Topinka, but yeah, the models were Bloch waves, two-dimensional Bloch waves.
that's right, and some random, I guess,
Yeah,
somewhat smooth random potential. Okay.
Yeah, so that was a linear model. So it's enough to kick this thing, but you don't have to have the nonlinearity on all the time. Some of the models I showed with the Josephson junction and then the triple well, Bose Hubbard 2 well and triple well, the nonlinearity was on all the time in there, exactly. But in some sense, maybe it's
not essential.
It's not essential. We did actually look at a kicked model for the triple well and actually for the double well. I didn't show them, but you can also get caustics there. Yeah.
Thank you.
So they certainly, yeah, you can either put the nonlinearity into your initial conditions. So start with a wavefront that has some sort of corrugation in it. So it's sort of the wavefront has passed through some medium that's produced some corrugations, or you can get that effect like in the Josephson junction, you have this focusing effect given by this cosine potential, if you like, that plays that role. So you can then start with perfectly flat wavefronts and so either way you put this sort of corrugation of the wavefront in, you're going to get caustics coming out.
Thank you. Any last question, maybe, if there is one? There isn't. Let's thank Duncan for waiting.
Thank you very much.